Welcome everyone, Chemistry 1007. This should be the last video for Chapter 9. We're getting into molecular orbitals. Molecular orbital theory, we're only going to look at diatomic molecules at best, be it like O2, N2, helium-2, which does not exist, by the way, and we can prove that with molecular orbital theory. So we're looking at a very limited scope of expanding our understanding of bonding in molecules. We learned about the atomic orbitals extensively, SPD and F orbitals, and how those work in atoms. And then we came to the valence bond theory and overlap and hybridization. For example, we would have a hydrogen a hydrogen with an s orbital overlapping with an sp3 orbital of carbon. Or we have hydrogen with an s orbital overlapping with a sp2 atomic orbital that's hybridized. Or we have a hydrogen overlapping with an sp orbital in carbon, all in carbon, and some other examples that were not carbon. But now we're not doing this overlap. We're actually creating, it's a little bit more than hybridization. We're creating entirely new orbitals. And so this is called molecular orbital theory. And it will help us explain things a little bit better mathematically. And we're not going to get into all that. You just need to know that qualitatively and understand that. But molecular orbitals have characteristics that are similar to atomic orbitals, but different. But they do have the similar characteristics of only 2 electrons per orbital. That rule is going to stay the same. The electrons in the same orbital must have opposite signs. It can't violate the Pauli exclusion principle. Definite energy of orbitals, we have that, although it's better defined in molecular orbital theory. It will help us understand magnetism, and it will help us understand spectral properties such as UV vis light emission. And it gives better numbers than the other theories. Okay, it gives us more exacting numbers. It's also wave function based, which comes from Schrodinger, quantum chemistry, quantum light features, as opposed to classical waves. We are now going to be able to explore that. And there's definite energy of orbitals that can be determined from MO theory. So molecular orbitals differ from atomic orbitals because they represent the entire molecule, not a single atom, not just a hybridization of carbon at the center and then hydrogen coming along and overlapping with its s orbital. And there's a kind of a just an overlap, or even a hybridization of another atom, such as carbon, that gives you sp2 and sp3. We are going to have an entirely new orbital produced. So whenever 2 atomic orbitals overlap, 2 molecular orbitals will form. Okay, that's how we're going to explain bonding now in these diatomic molecules. Okay, we're not going to go much beyond that. So don't try to transpose this onto larger and larger molecules. Don't do that at this time. For example, we're also going to find out there's going to be bonding orbitals and anti-bonding orbitals. For the first time ever, you've never heard of the concept of anti-bonding until today. Anti-bonding really contributes to the destabilization of that molecule. And if you have too many anti-bonding orders, we're going to see through a calculation that your molecule may not exist. For example, helium, we'll understand why helium-2 does not exist on Earth. Helium-2 we can prove it through molecular orbital theory that helium-2 or diatomic helium does not exist, and we'll see why through a mathematical calculation, where we'll see oxygen O2 does exist through a mathematical calculation to confirm that. And physical reality affirms that diatomic helium does not exist, and diatomic oxygen, of course, does exist. And molecular orbital theory helps us explain that, along with magnetic properties about how a molecule can be attracted to a magnet and how a molecule can be repulsed by a magnet or have no effect at all. Bonding orbitals are constructive combinations of atomic orbitals. A little bit like hybridization theory, but we're getting total new molecular orbitals with different names we haven't seen yet. We have anti-bonding orbitals that are destructive combinations of atomic orbitals that raise the energy. And when electrons are in anti-bonding orbitals, they're very destabilized. We can have some electrons in anti-bonding orbitals, but we have to have more electrons in the bonding orbitals for that to be possible. And it will give us some idea about the energy of that molecule. The more anti-bonding orbitals that are filled, the more likely that that molecule might be somewhat reactive. We also have what they call a nodal plane, where the electron density through that plane is going to be exactly zero. We've seen nodes, but we haven't seen the idea of nodal planes. So molecular orbital theory, overvalence bond theory, or overlap models, why would we want to even consider this model? It provides more comprehensive understanding of the molecular properties, a little bit more so than valence shell electron pair repulsion, although that's still helpful as well. We also can use rules from atomic orbitals such as Pauli exclusion principle and even the Hund's rule, where if you have degenerate orbitals, you want to fill all of those orbitals at least with one electron before you start pairing them up. So review what Hund's rule means and what Pauli exclusion principle means. And so magnetism is explained through molecular orbital theory and the diagrams that we're going to look at briefly. And then we also have light emission bands for UV-Vis spectra. So molecular orbital theory, just to give you an overview, we have it's not really hybridization, it's a complete morphing into these new orbitals, and they're formed through a linear combination of atomic orbitals. They call that LCAO, a linear combination of atomic orbitals. These orbitals can be bonding, anti-bonding, or non-bonding. We also have, that's kind of lone pair electron stuff. So if we look at energy levels, molecular orbitals exist at specific energy levels and can be filled according to the Pauli exclusion principle and Hund's rule that we learned all the way back with atomic orbitals. So this new theory we're introducing that did come after valence bond theory and hybridized models is also compatible with other things as well. So molecular orbitals, what is that all about? Well, of course, electron density has got to be involved. We have waveform or constructive combinations of these orbitals, and we know that we've talked about sigma orbitals or sigma bonds. This is a little bit different than a sigma bond. We're calling these sigma molecular orbitals, which will contribute often to the stability when it's not an anti-bonding order. It's not of the anti-bonding orbitals. And so let's just take a very simple diatomic molecule, which is very important, is hydrogen and hydrogen coming together to form H2 gas. And these energy levels are relevant. This y-axis is the lower energy down here and the higher energy up here. So if we take two of these atoms, they morph together and these molecular orbitals come together to form this H2 molecular orbital that's called the sigma 1s. And then we go up here and we have orbitals here that form that are divided. They're not, the electron density is actually cut up in half, and they're called sigma 1s star. And those are anti-bonding orbitals. Whenever you see a star next to the name of the orbital, in this case it's sigma 1s, sigma star 1s, that is anti-bonding. And those orbitals, when occupied, can contribute to the reactivity or the instability of that molecule, meaning that it may fall apart. Hydrogen each one has one electron to donate. And so we can have this, what they say, constructive combination leads to the bonding H2 molecular orbitals. That is a sigma 1s. The destructive combination leads to anti-bonding H2 molecular orbitals. Just like Schrodinger's equation talked about the overlap and stability and electron density in some places and not in others, this model takes that into account. When these orbitals are filled, it will contribute to the destabilization of this molecule. We have two atomic orbitals, so we have two molecular orbitals. This is the first molecular orbital, sigma 1s, that's formed, and then the second molecular orbital is sigma star 1s. We know that each orbital can hold 2 electrons, and so we have 2 electrons, and they all go into the lower energy orbital. So there'll be 2 electrons that will be anti-parallel to each other, with the spins are different, plus 1/2, minus 1/2, one spin going up, one spin going down. So the electron density is only placed here. We don't end up with any electrons in these orbitals. Now, if we were to try and put 2 extra electrons in here, like if we were to try and make, say we decided to think about this. This is kind of fun to think about. We know hydrogen 2 has to have 2 electrons. But say we got fancy and we decided to add 2 more electrons. We tried to do this. We want to know if this exists. So we have this hydrogen gas molecule that's going to have 4 electrons. We've never seen anything like that. Is that even possible? Well, we can look at our prediction through the molecular orbital theory. And this, of course, is now going to be 2 minus, because we added 2 extra. We didn't add any extra protons. So now we've got this 2 minus charge on this molecule. And we end up adding 2 electrons to this anti-bonding orbital, and we're going to end up canceling out the bonding order, and we'll look at the calculation on this. But this diatomic 2 minus hydrogen gas cannot exist. It's destabilizing. It's too high energy and will fall apart. So the molecular orbital diagram and bond orders. So let's look at this a little more closely. Again, this is a hydrogen atom coming together with a hydrogen atom, and they're at a higher energy. The atomic orbitals are at higher energies than this sigma 1s, which is a lower energy. This is at a lower energy than the atomic orbitals. And that explains why it would even happen. There has to be a reason why hydrogen atoms wouldn't just want to float around with themselves. Well, the molecular orbital theory explains that. You have sigma 1s that is at a lower energy. The molecular orbital sigma 1s is at a lower energy than the atomic orbitals of the hydrogen atom. But we also have a second molecular orbital formed up here that is at a lot higher energy than the atomic orbitals, and a higher energy than this lowly placed molecular orbital, which contributes to the stability. This is the bonding. This is the bonding electrons, and this is the anti-bonding molecular orbital with the anti-bonding electrons, if any would go in there. And if we added those 2 extra electrons, we would cancel out the stability of this H2 molecule, and it wouldn't go. So keep your thoughts kind of simple on this, because we don't want to go much beyond diatomic molecules. How do we calculate the bonding order? Really simple. The bond order is 1/2 of the number of bonding electrons, which in this case is going to be 2, minus the anti-bonding electrons. And in H2, there are no electrons, so we can just put 0. So it's 2 minus 0, and we'll just get 1 bond. And if we look at the covalent bonding of H2, there is a line there with 2 electrons, and it just has 1 bond, and this is 1 bond. So we can even predict the bonding order, okay? Now, if we had those 2 electrons in here, let's put those in here, and I make this crazy molecule called H2 minus, and I added 2 extra electrons. This 0 would become 2, and now it'd be 2 minus 2. That would be 0. So H2 2 minus can't exist, and this will fall apart. So we can't do that. So these are energy level diagrams. Never forget that the energy is a y-axis value, and it's relevant to this is more towards 0, and this is more towards higher energy. So don't forget that. And these are the atomic orbitals, and these are the molecular orbitals, right? These are the molecular orbitals that form from the atomic orbitals, and they're not really hybridized. They are actually new orbitals. They are molecular orbitals. It's a little bit different than valence bond theory and overlap theory. Can He form? Can helium gas form? Well, I told you no, but it's for the same reason that H2 diatomic hydrogen with the 2- charge could not form either. But here we have helium, and helium, each helium atom has 2 electrons to contribute. Remember, there has to be a reason for even trying this, and this sigma 1s, this bonding orbital, you can put two of the 4 electrons that are now in the molecule in here. Now, don't forget your Lewis structure idea, because when you create Lewis structures, you add up all the valence electrons. When you create Lewis structures, you add up all the valence electrons, and therefore you know how many valence electrons are in the entire molecule when you work on VSEPR theory and structure. Here we have 4, so if helium-2, we can get 2 of them in the bonding order, which is good for stability, but then we put the other 2 in this sigma star 1s, which is the anti-bonding molecular orbital theory. We do the math to find out if there's any bonding power whatsoever, but it's 2 electrons minus 2 electrons divided by 2, 0 divided by 2 is still 0, and so this does not form. Helium does not exist using molecular orbital theory. Now, helium may exist under some very special conditions, but not typically. So, paramagnetic versus diamagnetic substances. Okay, what is this? This we can kind of look at this from the atomic orbital perspective, but we don't usually do that, and we haven't done that yet. We could look at atoms to find out if they have any unpaired electrons, just as atoms. And here it looks like we have 3 unpaired electrons. We got S occupied and 3 p orbitals, and they all have 1 electron in them, meeting the Hund's rule, so they're not pairing up, because there's other degenerate orbitals to be filled before they could pair up. If we added a 6th electron here, they would pair up. But if we're adding 2, 3, 4, and 5, they have to separate into degenerate orbitals and spread out as far as possible. And they're all in the same direction too, and they're unpaired electrons. So if you got unpaired electrons, you have some attraction to a magnet. You have some weak attraction towards an external magnetic field. That's going to be very important for nuclear magnetic resonance. Remember, this is just atoms. We haven't got into the molecules just yet, which is even easier than this. And then we have the diamagnetic property. The diamagnetic property is when all these electrons are paired up. It cancels out the ability to be attracted by a magnet. In fact, it may even be slightly repulsed by the magnet. There is no attraction for a diamagnetic atomic species or a diamagnetic molecule, which is more important in this case, because most of the time we don't deal with just atoms anyhow, and unless we're dealing with metals like iron, but we're dealing with just atoms to get us started here. And because these are paired up, it cancels out any magnetism it might have. So no magnetism here, but this has magnetism because of the unpaired electrons, and therefore it has a slight attraction to a magnetic field. Let's look at O2. How many electrons are in each oxygen atom? We know that to be 8, and we know if we have 2 of those, it must be 16, right? It must be 16. So if we have O2, we ask the question, is it paramagnetic or diamagnetic substance? Okay, well, we see this diagram. This is kind of new to us as well. So let me go through this a little bit, and hopefully it'll make good sense, and we'll learn lots of new things. Now, remember, for every atomic orbital, there must be equal number of molecular orbitals. So that makes our life a bit easy. So if we have 1, 2, 3, 4, 5 atomic orbitals, we must have, and then we have 2 oxygen atoms, so we have a total of 10 atomic orbitals. We must then have a total of 10 molecular orbitals, and we'll see how that works in a second. But this is an oxygen atom and its atomic orbitals. All of this is the atomic orbitals of oxygen, as you would predict. 1s2, 2s2, and 2p4 is the electron configuration. So if you don't know the electron configuration of one oxygen atom, go back and do that. Again, 1s2, 2s2, and 2p4. And then we have a second oxygen atom, and it has the same electron configuration. But then in the center, they create these molecular orbitals that form out of the linear combination of the atomic orbitals. And we start placing these. Now, remember how many atomic orbitals does each atom have? 1, 2, 3, 4, 5. Not electrons, we're looking at atomic orbitals. 1, 2, 3, 4, 5. So we should have 10, we should end up with 10 molecular orbitals that can be created. They may not all be occupied, but there must be at least 10 that are on our chart. And there's 2, 4, 6, 8, 10, 12, 14, 15, 16. Oh, wait a second. We added up the electrons. So we have 16 electrons. 2 times 8 is 16 electrons. But we have 1, 2, 3, 4, 5 atomic orbitals for each oxygen. So 2 times 5 should be 10 molecular orbitals. So let's see if we have 10 molecular orbitals. Let's not count the electrons. Let's count the orbital. There's 1 orbital, 2 orbital, 3 orbitals, 4, 5, 6, 7, 8, 9, and then 10. There we go. We have 10 atomic orbitals. And so every time we make a bonding atomic, every time we make a bonding molecular orbital, we have to make a anti-bonding molecular orbital, and it's got a star. Every time we make a bonding, now we got a sigma 2s bonding orbital. So we must make a sigma star 2s bonding orbital. And then we go up into these higher levels that you've never seen, and you kind of have to memorize them. I don't think I just kind of want you to understand what's going on here. I don't know if you need to know the name. If it's on a test, I would give you the orbitals and let you kind of decide if we need to do that on the test. Look for the study guide coming out for the new material on the final. But we have the sigma 2pz, we have the pi 2px, and the pi 2py, and they're all bonding orbitals. But if we go up higher, we have the pi star 2px and the pi star 2py, and they're both anti-bonding orbitals. And then we have a sigma star 2pz. And so it's kind of symmetrical with respect to the anti-bonding orbitals. This is the first time that you've ever seen this. There's there is not enough electrons to occupy any of the sigma star 2pz, which is it's the highest unoccupied molecular orbital. They call that highest unoccupied molecular orbital. Okay, highest unoccupied molecular orbital as opposed to highest occupied molecular orbital. So there is nothing in this at all. Okay, now we can add up what is the bonding order of this. We have to add up all the electrons that are in the bonding orbitals versus all the electrons that are in the anti-bonding orbitals. So all the orbitals in the bonding orbitals, the ones without the star, 2, 4, 6, 7, 8, 9, 10. We got 10 bonding electrons in bonding molecular orbitals. Now we have to add up the anti-bonding number of electrons. So we go to the first sigma star 1s, there's 2. We go to sigma star 2s, there's 2 more. And let me switch to the laser pointer. We go to sigma star 2s. So we have 2 here and 2 here. So we have 4. And these are all bonding orbitals, but we have pi star 2px and pi star 2py that have 2 more electrons. So 2 plus 4 is 6. So we have 10 minus 6, which is going to give us a 4. We have to take half of those, and half of 4 is 2. So we get 2 as the number of the bonding order. And guess what? That actually tells us, let me draw this out for you. If we have an oxygen, and we wanted to draw, it matches the Lewis structure. And we end up with a sigma bond and a pi bond, or we'll call this a sigma bond and a pi bond. Now, if you want, you can add up all there's how many valence electrons of oxygen is 6. There's 12 electrons between the two. And if you want to do the Lewis structure with that, go ahead. If you need help with that, come see me. Well, we know we have 2, 4. We have -4 electrons in those two double bonds. In those two bonds, one is a sigma bond and another high energy pi bond, which can, in theory, resonate, but maybe not so much here. Oxygen is pretty stable, but well, it's also very reactive. Oxygen is one of those things that's actually, we have to breathe it, but it does have some reactivity. We're left with 8 electrons, and so we need to probably split those electrons up. If we divide them into by 2, because electrons like to travel in pairs, we get 4 pairs of electrons. So we can put 2 pairs of electrons on each oxygen. So 1, 2, 3, 4, 5, 6, 7, 8, and that's our oxygen species. And there is no charge on this, but what if I did something like this and I said it's O2 minus? Now I would have 13 electrons. I'd have 13 electrons, wouldn't I? 13 electrons, and then I can add an electron here, right? I can add an electron there. Uh, and so on. Well, it wouldn't go here. That's the wrong place to place it, because this is very high energy. We would want to put it in this lower orbital. So guess what? So we have O2 minus, and remember, oxygen, O2 is paramagnetic because it has 2 unpaired electrons. If we go to O2 minus and we add 1 electron, and now we have 13 electrons total in the valence shell, we actually have 16, 17 electrons for the total atom. And so from that perspective, it's also still paramagnetic because it now would only have 1 unpaired electron, and it still would be paramagnetic. So it still would have some attraction to a magnet. But let's suppose we say we have O2 minus, 2 minus. Now we have to add 1 more electron. And if we have O2 minus, guess what? We have no more unpaired electrons. These are all paired up. We have 0 unpaired electrons, and therefore it goes from being a paramagnetic species to diamagnetic, and it sort of repels a magnet or is not attracted at all to a magnet. So you can see the magnetism and other features can be determined from molecular orbital theory. And that's the end. That's molecular orbital theory. Maybe look at N2 gas. See how you do with looking at N2 gas as in a molecular orbital theory, with nitrogen having 7 electrons total, and you place 14 electrons because you have 2 nitrogen atoms. See how that works. And I appreciate you watching the video. This will do it for our video series for chapter 9. We are done. Have a good evening.